Yeah, hello, Katrina.
Hello, how are you doing today?
Doing great,
Reminder.
Katrina.
How are
Thank you.
you? How are you?
Doing great, Katrina. How about you?
Oh, I'm good, thank you.
Good, good.
Getting used, we had to put our clocks back an hour here, so
Yeah,
getting used to the new time zone.
too early for you in the morning.
Yes, but that's okay. This is rather normal for me.
Yeah.
It's evening for you, I think. Is that correct?
Yeah, 6 p.m.
Mhm.
So we are waiting for other guests to join.
Yeah, oh, no problem. No problem at all.
Hello everyone. We'll start the session in a couple of minutes. Thank you. Welcome everyone. Good evening to all my fellow Indians and a very good morning to Ms. Katerina. First and foremost, I would like to thank you all for joining us today for this amazing event. I, Meghna Surampudi, will be the host for the day. Firstly, I would like to congratulate you all on taking the step to absorb a unique experience. I can envision the spirit and passion you all have towards learning something fresh and unique which could truly upskill your streak. I assure you all that this electronic product build-a-thon is not for beginners. We feel honored to have with us today Ms. Katharina, co-founder of Voltera, Canada, Mr. Ramakrishna Dasari, CEO of Eftronic System Private Limited, Dr. Ravi Gujula, Chief General Manager, Technical, APSSDC, Professor Ravi Kumar Annavarapu, IMMTD, past chairman of IETE, and Mr. G.S. Srikanth, founder and managing director of Albit Technologies, and Mr. Amarendra Katkam, founder and CEO of SmartBridge and SmartInternz. So, without taking much of your time, please permit me to start the program. Electronic Product Build-A-Thon is an exclusive skill building initiative by SmartBridge in association with Voltera to enable students and educators with electronic circuit designing skills. This program is a learning by doing event packed with hands-on training, project development, and mentoring sessions powered by SmartInternz and Voltera. So, boys, girls, and ladies and gentlemen, can you foresee the amazing experience ahead? Yes, I do. Take a deep breath to dive deep into one of a kind learnings. So, without further ado, let's acknowledge the presence of our guests of the day. I consider it a great honor to introduce our uh, guest of honor of the day, Ms. Katharina, co founder of Voltera, Canada. Katharina is a nanotechnology engineer who specializes in the development of nano-functional materials. In 2013, she co founded Voltera, which has disrupted hardware innovation through additive manufacturing. Voltera's electronic 3D printer was ranked Popular Science Top Innovation of the Year and was the first Canadian product awarded the International James Dyson Award. The Young company holds the 23rd spot in Canada's fastest growing companies. Ms. Katharina, you're the lead now.
Thank you very much. Can everybody hear me okay? Just give me like a yes in the chat.
Yes, Katharina.
Yes, we
You
can hear
me
you.
okay? Excellent. All right, I'm going to go ahead and I'm going to share my screen as well. All righty. All right, everybody can see my screen as well. It should say Voltera, just the front screen of my slides over here. So for starters, thank you everybody for joining me today. It's great to be kind of speaking in front of so many people. It's my honor, really. I was in India a few years ago now, giving a similar type of talk, and I had a really wonderful experience over there. It was really great to see all of the basically academic establishments that you have over there and the dedication that you have towards academia. I went to visit many IITs while I was there, the triple ITs as well. And so I just had a really great time while I was there. And I was supposed to be making my way back actually, but kind of COVID put a whole big stop to that. But luckily we've partnered now with SmartBridge, who could hopefully help towards bringing some of the educational experience that we have as Voltera to India without my physical presence needing to be there. So thank you very much for all joining me. So today, I primarily want to talk to everybody about hardware, primarily, and that's kind of because hardware is absolutely everywhere. So those little green boards that you see, whether they're in your cell phone, whether they're in your refrigerator, your laptop, your Fitbit, no matter what it is, they completely control our world. Those little green boards, they look simple, but they're actually relatively complicated. And so, these boards actually, as abundant as they are, and basically everything that we use from our phones to our laptops, they're actually really hard to get your hands on. And I experienced this kind of firsthand being an engineering student. I was a really keen engineering student. I was a big nerd, if you will, involved in all of the different types of electric car clubs, Mars rover clubs, everything that you can imagine. Except getting access to these boards was actually very difficult, because essentially as the designer, you're stuck essentially sending design files off, very often overseas to China, waiting weeks to get those design files back, just to find them and realize that there's a mistake on them. And you have to start that process all over again. So it's a very frustrating experience. And this is why Voltera was born. This is why we started this company in 2013, was in an attempt to accelerate hardware development for students, for academics, as well as industry professionals, so that we can really kind of speed up this process. This is just an example of one of the factories that you'll see located in China that spits out these circuit boards, thousands of them, absolutely thousands of them, within a matter of 5-minute intervals. And so, in 2013, when we had started this company, myself and my co-founders actually ended up moving to China so that we could build faster. Can you imagine that? We had to physically move ourselves to China, where all the product was, where everything was happening, so that we could actually build product faster. And we kind of realized a lot from that experience. And that's that we never wanted to do it again. We really wanted to take that experience of being in Shenzhen, China, and having product accessible to you anywhere you went, and bring that back home with us and bring that back to the rest of the world. Essentially put the factory on your desktop rather than having to actually go to the factory in order to develop product quickly. So this is just one of the factories that we're speaking about. If we look at sort of the circuit board manufacturing industry as a whole from here on in, I'm going to just refer to it as PCB. The PCB industry, okay, printed circuit board industry as a whole, it's a $75 billion market, okay, for circuit board fabrication, and it grows by 10 billion every single year, okay. And it's incorporated in absolutely every industry, every discipline, everything from the Internet of Things to renewable energy, to renewable energy, right? We are now using technology to solve the problem that we've created with the environment and technology, but we still need technology to solve this problem. Mobile energy, autonomous vehicles, energy storage, advanced robotics. So no matter where you look, PCBs are there. And so we need people that can build them efficiently, and that can essentially help in contributing to this booming economy of $10 billion every single year growing. And the industry that I'm going to be talking about particularly today is, of course, advanced manufacturing. And when I speak about advanced manufacturing, of course, I talk about additive manufacturing. So 3D printing, desktop printing, anything along that line, which we're going to be getting into in a little bit. Now, here's the problem that I ran into personally as I was a student with my co-founders, as I'm sure many of you have also run into. If we have any students in the audience, which I know we have today, if we have any young entrepreneurs in the audience, which I know we have today, I know that you're probably used to seeing this process right here. You have an idea. You want to bring a hardware product to life, okay? So of course you start the idea off with a schematic, a rough layout of what it is that you want to do, okay? From the schematic, you build the prototype. Now, the prototype is where we often struggle. We struggle at the prototype because we have nothing that is representative of the final manufactured design. So when it comes to the prototype, you're left using things that look like this, breadboards. And so you're kind of crossing wires all over the place and soldering wires all over the place. Maybe you're using perf boards. Maybe you're using CNC machines or desktop size equipment to drill away to create a prototype. But the bottom line is, when it comes to building the prototype, it's rarely representative of the final manufactured product. And you see, I've gotten over here the final board that you would actually get from a factory. Now, this is a big problem, of course, when it comes to entrepreneurship. Creating something that is unrepresentative of what the final product is going to be is a big, big issue. It's an even bigger issue for students, okay? When you're learning how to design prototypes that at the end of the day aren't going to be representative of what you're going to be putting in the product, we've discovered that it's actually a really big problem. I travel all around the world to kind of find out what students are learning, what they're learning in school. And this seems to be kind of unanimous. And now in some situations, we don't even see what the final manufactured product looks like, okay? In some situations, students will have the idea, they'll create the schematic, and they'll just design the prototype without ever having been exposed to what a real PCB looks like that might be in your phone or your laptop, which of course makes a big problem for the industry. And in some situations, believe it or not, I've even seen this happen, where there is no prototype. So students are only exposed to having an idea, creating a schematic. They look at it a lot of textbooks, which, don't get me wrong, textbooks are great. They'll learn about resistors in series, resistors in parallel, and all of those concepts, but they never actually get to the practical learning bit, where they're taking this knowledge and they're putting it into something practical that will eventually be used in something that will be a manufacturable design. So this leaves us with a really big problem, people. And that's that millions of engineers graduate every single year not being able to build anything, okay? And I used to be one of them. Okay, 5 years of schooling, and I graduated never actually being able to build a properly functioning PCB. Can you imagine that? 5 years I studied, electrical engineering concepts, schematics, how to build prototypes without ever actually building prototypes, let alone truly understanding what actually goes into an industrial design. And so this creates a really, really big problem. I mean, you take me, a student like myself back in the day, I just graduated. I spent a good amount of my time and money on school, inevitably to graduate, and I can't actually put that into something practical. And so this creates a very, very big skill gap. Now this here that I've quoted, this quotation down here, oh, sorry about that. 15 million students entering the workflows each year, okay? In corporate India and research institutes agree that 65 to 75% are not job ready or are unemployable, okay? This is not just a problem in India. This is a problem everywhere in the world. So I have become obsessed with this problem. Of course, from a hardware standpoint, I've become obsessed with this problem. And everywhere I go in the world, I talk to the industry and I talk to academics. And one thing that I've realized is that the industry as a whole, no matter where you go in the world, agrees that students are not ready to enter the workforce. And a big, big problem is because there is a lack of practical hands-on experience. So there is a great job being done in teaching theoretical knowledge, which is fantastic and which absolutely needs to be applied. But there is a lack of hands-on experience that is truly representative of what you would be doing in the industry or creating industrial products. And so this creates a very large skill gap that is felt absolutely everywhere in the world. I fell right in the middle of it as well. Now this, while I was, finishing up school, worrying about the skill gap and everything, wondering what I'm going to do, it was kind of during the time of the maker movement. The maker movement that was largely inspired by 3D printing. And so, this was just starting to kind of pick up speed in 2008 when I was entering engineering school, and it was well within realms when I was leaving school in 2013. But for now, right now, you had this really very kind of incredible movement that was happening, where you had 3D printers going from being industrial-sized machines that were, reserved for, corporate America that had large capital budgets, and they were shrinking them to these desktop-sized instruments that were becoming more cost-effective for everybody. And so now they were being kind of distributed for anybody to use. And I remember this time very, very thoroughly, because I remember looking over at my mechanical engineering comrades and kind of being very jealous of them, because, for the first time, they were just going from having a CAD on their screen to having something physical printed in their hands within a matter of an hour or so. And the incredible part was what they were printing was actually representative of what would be the final manufactured design. So that's the biggest, that's the language that I'm using here today, folks, is representative of an industrial product. Okay, that's at the end of the day the most important thing to the industry. And so this was kind of fantastic, but when it came to circuit boards, we were still left in the slow lane. Add on to that, of course, software. I mean, software, this has been around for decades. This is nothing new to people, but software has become faster and faster. Compile times have become quicker and quicker. And this has created essentially a giant boom of software companies exploding all over the world, especially out of Silicon Valley. But it's not a coincidence that you have so many software companies that have been popping up all over the world, because the barrier to entry to software is actually very low. You need a software program, and you need to be a software developer, but the costs are low. And furthermore, you can see if your code works at the click of a button. Okay, so all you have to do is write your code and press that compile button, and you can see if it works. And if it doesn't work, no problem. You just do it all over again. Okay, you don't have this same barrier to entry like you do with hardware products, where if you make a mistake, it's a very, very big, very costly mistake. Okay, so while the maker movement was in full swing, we had 3D printers that were becoming miniaturized. We had access to sort of these mechanical products that we can physically touch within an hour. We had software just getting faster and faster, and this explosion of sort of software companies popping up all over the place. PCBs still kind of looked like this. So they were still a bit of a mystery. You could go from an idea to a schematic to sometimes a prototype. Rarely could you actually see what something that was production ready looked like. But it was still a very, very painful field to be entering and to gain practical experience into. And that's why in 2013, upon graduating, myself and my co-founders, we created what was known as a 3D printer of PCBs. And so we designed the Voltera V1.
Katrina?
This was the world's first 3D printer for electronics, so for PCBs, okay? It's a little machine.
Sorry to interrupt. Hello. Hey, sorry to interrupt. We'll just wait for the other guests also to introduce themselves, and then we'll just start getting into the details.
Yeah, sure.
All right. Thank you so much. Ahmad, if you can take the lead, that'd be great.
Meghna?
Yeah, sure. I'm on it. Katrina, can you share the screen?
Oh, yeah. Stop share?
Yeah.
Yeah. Okay, go for it.
Yeah. Thank you. Thank you so much.
No problem.
So, thank you so much for bringing up the facts into limelight, Katrina. It's really appreciated. Now, I'm profusely elated to introduce our honorable chief guest of the day, Mr. Ramakrishna Dasari, CEO of Eftronics Private Limited. He is the founding CEO of Eftronics Systems Private Limited, established in 1985. He is instrumental in Eftronics' growth and in positioning it as one of the India's smartest solutions company. Eftronics is now a leading provider of smart solutions for railway signaling, smart cities, smart buildings, and industries. He is the architect of one of India's largest IoT networks built for Indian Railways, with more than 6 million things connected across 9,000 locations. He is a continuous learner and a thoughtful leader. Under his leadership, Eftronics has innovated more than 50 solutions for different domains. By continuously growing Eftronics, Mr. Ramakrishna has proven to Indian industry that with the right aspirations and sincere effort to deliver value to the customers, it is possible to be successful, and location doesn't matter at all. He is involved in various social development activities for improvement of academics and industry. Presently, He is the immediate chairman of CII AP State Council and IEEE Guntur subsection. Mr. Ramakrishna Dasari, you are the lead now.
Good evening to all of you.
Good evening,
Is
sir.
I am yeah. Is it I am audible?
Yes, sir, you are audible.
Thank you, Katrina, for introducing all electronics, and it makes me to look back into my earlier days in college, where I used to have some multimeter and start making a transistor receivers and the tape recorders with the transistors way back in 1978. That's where I started learning electronics at that point of time. Now, from that to the today, there is a lot of change happened in the electronics. What we are seeing is a large scale integration in the chips, which really makes me to look into how to make any product like what we used to play with each transistor or the resistors. But today, is it possible for me to play the same way as you showed in some of the smartphone? I feel it is almost like a impossible task for me to experiment the things like what we used to do and play with that. Now coming to the what is the challenges and what are the opportunities and how the electronic industry, I talk more in context with the Indian industry rather than world. Of course, the world also moving, but the more from the Indian challenges point of view. What happened in the last, say, 3-4 decades, basically, the majority of the electronic industry started growing, whether it is in Japan or USA or even Europe or Korea or Taiwan, all these countries, they are able to have more of a chip manufacturing things in their countries, but they are able to grow much, much better compared to what happened in India. Unfortunately, India, they tried to make some silicon chip. To the situation, what is the possibilities how to build the Indian industry, especially in electronics? I try to classify the electronic industry in maybe 2-3 directions. One is the consumer electronics, where all our PCs are the monitors, TVs, and cell phones, and lot of other stuff where the large number of integration and the large volume of manufacturing happens across the world. That is the area where I feel, though there is a huge consumption in India, the valuation by the product in India is not even 10 to 15% by the people. That is where entire chips and the circuit boards are getting from the, whether it is China or other countries, and only assembling the things happening. That where we have very, very less opportunity to grow. But there are the other areas where the industrial electronics or the medical electronics or the defense and aerospace, where there is a lot of opportunities there for building the various solutions, because that is a continuous operation, but the volume of the products are going to be very less. And now what is happening across the world is the entire thing is becoming a digital. So that is where, unfortunately, the entire world, in my opinion, not really changed the syllabi to the digital. Though the digital electronics and the entire thing is shifted to the digital, but still we are trying to teach more of a analog electronics, which few days back when I am interacting with some of the professor, I said, for me, the most worst, what is called the subject or the whatever called the engineering syllabi is electronics and communication, because 70% of the syllabus are not today's need. It is all we can put into the dustbin, and only the 30% may be used, even that too in a not in perfect way. So what is that today missing is the digital electronics, and how really the algorithms were built and how the circuit design is done, whether it is in a FPGAs or whether you are talking about parallel processing or multi-core processors, and how the today's entire design is go around the say hardware. So this is where really I feel is a biggest challenge which every young engineer is facing. For me, most important as an entrepreneur, and when we want to hire the people, I need to train the people in a digital electronics. So it takes at least 2-3 years for them to understand the entire digital electronics. After that, they may be able to design some new things. So this is where really the Indian, the training or the colleges or the things, how to build an algorithm. That's where I feel this algorithm building is the thing which I feel has a long way to go, and it has a more and more value. People may think this is a software, but in my opinion, building an algorithm for a hardware which needs a totally different skills than the building a software for a financial applications and all. Today, the entire world is moving towards the IoT, where you are talking about a system of systems. Everywhere we are going to see microprocessors. Even the car may have hundreds and thousands of microprocessors, and they are all integrated. Basically, in our company also, we are able to build systems. Olden days, we used to put maybe 5-10 processors in one system. Today, we are talking about putting hundreds of microprocessors in one system. That's where how we communicate among the systems and how you build the algorithms. And again, the power of the CPUs are too high, where you can put a lot of genetics and a lot of possibilities to build really the new dimensional systems, which end of the day is able to take a lot of functions of the mechanical or other things. Like suppose olden days, the systems were built with the levers and all that levers and all mechanical activities were removed, and now all that will be achieved through the complex algorithms. So there is a lot of possibilities in that area, where if we are able to build the algorithms and simultaneously how to build the hardware towards that. So there's a small modules. And the biggest challenge today, which we are seeing, is how to integrate and manufacture and get free feel of it. Get feel of it is the most important. Unfortunately, as you rightly said, initially nobody is experimenting. All the things is that only theoretically somebody is reading or only mugging up, and only somebody may be thinking. But reality, majority of the time, people talk about the algorithm, also Googling the thing from Google and trying to get some algorithm from this and interconnect the algorithms. But that is not writing an algorithm. That's that there is a lot of knowledge is needed to learn around the algorithms and how to build the optimum solutions. One need to have a real insight into the thing, how really all hardware is working, how really the things inputs and outputs are changing and how fast it is changing. All this really fascinating, and when we are able to see everything is working, end of the day, we really feel thrilled about that. But that may not be seen, as you rightly said, about software. You can go on trying and trial and error basis, but hardware, when you are trying to work with embedded, of course, now with embedded, you have a now chance to modify the things up to certain extent, but not really. The entire thing cannot be changed as rapidly as it is possible. But today, I believe that there will be a lot of possibilities. We need to have unfortunately, when I look into the Indian industry, we don't have any course or something which is meant for developing or the product or solutions design or even manufacturing or even testing. These are all areas where really we don't have even proper infrastructure in the country, except from manufacturing of some of the high-end, say that to cell phones or some of the things. The largest production is there, but the real valuation in the country is very, very poor. All the equipment and machineries are all which we are importing from other part, from whether it's from Europe or Japan or China or somewhere. These are all making our industry has a bigger challenge is say everything, whatever we put in industry, we need to pay at least 8% to 10% is a interest in our country. That's one side. Other side is everything is dollar converted into the rupee. Because of that, again, the cost of any technology is very costly in India. Other side is all that depreciation and all, again, the knowledge to use and the best practices, all that are missing. Because of that, now there is a lot of gap, but the Indian government want to give a lot of subsidies and lot of things. Everybody wants to bring electronic production into the country, because the biggest thing after our oil imports, second highest import is electronics. That's where our lot of foreign currency or the GDP direction or the balance of payments, we have to pay a lot to the other part of the world without having imports. Maybe software is giving some imports, but that is not balancing our foreign currency. This is where our government of India want to give a lot of subsidies, even as high as 25-30%, to start the manufacturing in the country. There is a lot of opportunities there, but how to develop the skills and the things is a really biggest challenge. I think some of the technologies, whatever you are talking, are that type of practices may help in India to build the different manpower, except the software manpower, that to more low-end activities. Thank you for giving me opportunity to share my thoughts. As you are all talking, IoT is going to be the next gen technologies, Industry 4, where I feel a lot of experiments can be done in the country, if the government's also willing to do a lot of things. So I hope the future is going to be some opportunity. I don't know whether we are able to take up this challenge and grow as a country, because we have a lot of aspirant young generations. How to nurture them and how to bring it to the aspirant to grow in their future career. Thank you, and all the best to all of you.
Thank you, sir.
Thank you for best.
Yeah, first of all, my sincere thanks for joining this session, sir, out of your busy schedule. And your experience is always inspiration for all this young generation. I heard you in many academic councils and a lot of webinars. So it's always motivating for the young generation to get into this field, especially electronics product development field. It's growing like anything, and government policies and initiatives like Make in India and many other skilling programs are like supporting this growth. And thank you so much, sir. And we look forward to work with Ftronics in future. Love to have a lot of advisory recommendations from your side to promote electronic product development as a great skilling requirement in academia. Thank you, sir. Thanks for joining this session.
Thank you. Thank you. All the best.
Thank you.
Thank you for your inspiring oration, Dr. Ramakrishna. You bestowed us with valuable information. Thank you so much. So moving on next, Dr. Ravi Gujula couldn't join due to some force in business dropped by government officials. So let's move on. So I'm more than happy to introduce Professor Ravikumar Annavarapu, immediate chairman, IETE. Professor Ravikumar has 36 years experience in R&D plus teaching plus industry with 25 years of committed contribution, gratitude and association with IETE and past presidents, HFS, DFS and senior corporate members. He has held senior positions in space research, industry, engineering education and administration. Professor Ravikumar facilitates professional relationships and support the efficient execution of all office administrative requirements. Professor Ravikumar, you are the lead now.
Yes. Good evening, all. Am I audible, Meghana?
Yes, yes, sir.
Yes, Mr. Ravikumar, you are audible.
Yeah, thank you. This is an opportunity for me to see my Guruji, Sri D. Ramakrishna sir once again. He was my teacher in 1970s, 80s, early 80s. And he helped me in rigging up a small circuit at that time, 555 trimer oscillator circuit. And we were really working hard with a breadboard in our lab. And we are finding it very difficult to rig up a circuit with the loose contacts and everything. And we really lose this opportunity, present day appliances, technology, and resources available to students. I envy today's students because of the facilities they can just get on just pressing a tab, pressing a button. I would like to first greet Miss Katrina ji for giving us an opportunity to share this dais today. And I understood you started this industry with great idea to bridge the gap. This bridging the gap is very essential to really bridge the life, which is lacking all the world. And industry institution, two different things, engineering college and industry, they should be put together. I always believe in working hands-on training while studying. It is I always dream that it should be something like a course in medicine where medical college students are attached with hospitals. Every day, maybe after third year, they will be visiting as a doctor or premature doctor, hospital beds, visiting patients, following the investigations live and learn from it. But why this engineering is not like that? Unfortunately, it is not addressed, and I wish every engineering college should be associated with one industry. There are number of industries in the world, and engineering colleges should try, or industries also should give an opportunity for the budding engineers to share, to learn, to watch what practically is happening in industry. This is one idea I have. And with this opportunity to say a few words, I would like to take very shortest possible time by putting forth my presentation like this. In India, we have so many companies coming up with R&D centers in India to enhance the quality of their existing products. Whereas,
So, you want to share your screen?
No need. No.
Yeah.
So actually, this is to why this R&D is required in India is to boost the innovation, continuously launch new services and products. Multinational companies spending billions of rupees on research and development, which helps in enhancing the quality of their existing products as of now. After all, this R&D is required for any industry to develop the next gen technology. Whereas India, I would like to say, is offering talent at low cost. As a result of which, many of these companies are now planning to set up R&D centers in India, as the local industry is offering services from students. And as we all know, the world is looking at India after this COVID-19, and India is a vast market with potential of purchasing, potential of offering resources. It has got unlimited opportunities for businesses, industries, establishing R&D centers and launching products and selling products also. This is also coupled with proactive government, cost efficiencies, technical competencies, and a low-cost workforce. Mainly, India, we always can never compare the workforce cost with other countries. So setting up R&D labs, R&D centers in India will definitely boost investments, and employment opportunities, of course, they rise. Government initiatives and incentives such as Make in India, Startup India, and NPE, National Policy of Education 2019, and efforts to build electric vehicles in India, etc., along with enabling policies, are helping global firms to set up R&D industries in India. And this is possible only when there are people like what we see now on the screen, who contribute. What is more than required is not just the infrastructure and investment. What is required is commitment. So I see great committed people are there in India who can still contribute, and their dreams must come true. Then only it is possible to bring in various technologies and implement them in Indian land. And as it is dreamt of, instead of by being a buyer, India can always compete and become an exporter. And this is all possible by inculcating commitment into students, bringing them to the edge where the technologies are now surfacing, and orienting them towards this. So I request once again all the senior members who are attending this seminar to think about bridging the gap by encouraging the students to learn, giving them opportunities, the platforms at affordable and best costs. Thank you very much for the opportunity given to me, and I once again congratulate the organizers for holding this big program, which is helping pan India and the globe, where the students are attending from other countries also. Thank you very much.
Thank you for your oration, Professor Ravi Kumar.
Thank you so much, sir. Like it was always, I shared a lot of thoughts with you in developing new programs, especially into electronics and innovation centers across colleges, and having a lot of experience in space and the communication engineering. Definitely, we look forward to work with you in creating a great skilling programs for the academia. Thank you, sir.
Thank you, sir.
Moving on next, I take pride in introducing Mr. Amarendra Katkam, founder and CEO of SmartBridge and SmartInternz. Mr. Amarendra, the founder of SmartBridge, the man with distinct vision and a fountainhead of illuminating ideas, an idol of knowledge and experience and inspiration to all of us. His passion towards building an effective learning systems has made him relinquish his career in the central government sector to start the SmartBridge in 2015. Till date, the SmartBridge has enabled thousands of students and faculty on emerging technologies via project-based learning. He has received IBM Champion 2020, 2019, 2018 for his contribution to the community in building emerging skills. Mr. Amarendra, you are the lead now.
Thank you, Meghna. First of all, a very good evening to all the participants over here. We have faculty and student and even people from the makers hubs and makers industry here. So thank you so much for joining this event, and it shows your interest in building electronic product development skills. And my sincere thanks to Katharina for accepting a great program here, because we could able to create this program only with the support of Voltera, and we share your vision of building electronic product development talent pool in India and across the globe. So dear participants, like I just want to give an overview about the event and why we have brought in this particular program, because from 2015 onwards, we are closely working with the academia, especially the student communities and multiple departments and HODs. So because of thanks to Makers movement, it brought a lot of change in engineering community, especially in terms of establishing Internet of Things labs, electronic product development labs, and many students got introduced to the open platforms like Arduinos, Raspberry Pis, ESPs, and many other cheap boards which are available for the students. And by the way, the current engineering students are very lucky, because during my engineering time, we don't have such kind of boards. We used to work only with the simple components of electronics. So now you have everything off the shelf, just bring all the components together and build a circuitry. So, but 2015 to 2020, I can say like 2020, I have seen a lot of work done across academia, and many of thousands of students participating in various innovation challenges. It may be national level challenges like Smart India hackathons, and building beautiful, I can say, innovative applications in IoT, as well as variety of other products. But I see definitely a gap here, and most of HODs and faculties are now asking for what next. That is a question put to us whenever we visit the colleges. So every year they are building hundreds of projects with the help of Arduinos and Raspberry Pis. But what is the next step for the students and faculty? So that is where we see a gap in academia, as well as industry also looking for a specialized skill set, especially in terms of building the core hardware products, as well as the core firmware development kind of skill sets. So students are building innovative products, innovative prototypes, I can say, and they are ready to get into the next level. Industry is also looking for the skills in product development, and the firmware development, and even the edge computing is also coming into the picture. So many companies have, especially the semiconductor manufacturing companies, are coming up with a chipset where you can embed machine learning and deep learning algorithms directly on the chipset. So looking at this gap, and the request from the HODs and the faculty and the students who are coming to SmartBridge to convert their prototype into product, so we came up with an initiative along with Voltera to launch this electronic product build-a-thon event. It's just a beginning. We want to continue this as a series where students will be taken from the beginning, like a basic level of skill set in building electronic products, to the complex product development thing. And thanks to Voltera mission, especially Katharina, thanks for providing us a demo mission, and we have experienced the Voltera V1 machine. We have built multiple circuits on that, and it's such a very beautiful machine. I have seen other PCB printers in the market, but it has a competitive edge over all the PCB printers in the market. So we would like to introduce the Voltera V1 machine across academia, and train students and faculty through the electronic, the product building cycle. I can say it's a rapid product building activity, utilizing the PCB printing machines, and the knowledge which we are going to share through our SmartInternz platform. Thank you all once again for joining this session. We are going to have the 3 days of hands-on bootcamp on building the electronic product, starting from circuit design to the complete PCB layout and the Gerber generation. And we also show live how to print an electronic board, a PCB, directly with the Voltera V1 machine. And you will enjoy a mentor-guided electronic circuit development activity after bootcamp. We are looking for a great participation from all of you, and we are looking for a wonderful outcome from this particular event. And we also organize similar kind of events in future. Thank you all.
Thank you so much, Mr. Amar. So on behalf of the SmartBridge, I would like to thank you once again for kindly joining us, and would like to hand over the platform to Ms. Katharina. Katharina, the platform is yours.
Katrina, we love to hear your success journey after launching the Voltera V1 mission.
Thank you very much. Can you hear me?
Yes, Katrina.
All right.
Yes, we can hear you.
Excellent. I got very carried away. I got excited. It's good stuff. Okay, awesome. Wonderful meeting everybody here today. It's really great to actually see the amazing turnout that came today. I'm very, very impressed with it. This is one of the larger sort of academic-based events that I have to admit I've been to. So huge congratulations to our guest speakers and our co-hosts at SmartBridge for putting together such a large event. I do have to admit I've been to hundreds of these, and the turnout kind of has been outstanding. All right, I'll run through the rest of this so that we can kind of get to fun. So I was kind of right in the middle of just explaining to you the issue with the skill gap, and I'm happy that some of our other speakers have touched upon it. And recognize that it is indeed a problem. And I do want to say, part of the issue is simply that the industry just moves a lot faster than the institution. And I'm hoping that we can kind of change that with the proper tools that are going to be implemented to help the institutions catch up essentially with the industry. Let's go ahead and move. So we talked a little bit about the maker movement already. We talked about software. And essentially PCBs and hardware development still very much being stuck in the slow lane, which is very unfortunate given that it is essentially the brain of any hardware product. So kind of important a little bit. And that's kind of when we created this machine, which was, well, 3D printers are a thing. Except 3D printers allow you to print plastic, and there's not too many functional things you could actually end up doing with plastic. So what if we were kind of to set off on this journey to create the 3D printer of electronics? Seemed simple enough at the time, except it sort of ended up being an entire journey that took us all the way around the world and back, with the bread and butter of the material actually being in the chemistry. So I'm going to fast forward through all the boring stuff, but essentially at the end of the day, here is how the machine works, okay? And you're all going to have a chance to kind of get to use it and get to see it, which is fantastic. But it deposits what's a highly special silver nanoparticle-based conductive ink as the traces and the pads of your PCB board, okay? And this is kind of why this technology took about 3 years to launch to begin with. Because the secret sauce wasn't actually in the hardware or the software, it was actually in the chemistry. So depositing something that is metal, essentially in fluid form, that is fully conductive and has those properties that you need coming out of a PCB board. And so now, you can design your circuit board in whatever software you're already comfortable with, upload it as a Gerber file into the actual machine, just press print, and you have your PCB printed and ready to go. There is a 550 watt heater implemented inside the actual machine. So be careful with that because it gets hot in order to allow for a curing process of the conductive ink. And what that does is it solidifies it essentially. It solidifies the pads and the traces into silver so that you have solid conductive properties that are coming out of it, which is great. So really quickly, I can show you guys here how it works before you get to see for yourself. This is just a really quick promo video that we put together. Let me know if you can see it. All right. Comes with a drill head attachment so that you can drill vias for dual-sided circuitry as well. And there it is laying down the silver nanoparticle conductive ink. And the biggest thing here is that the final board is representative of something that's going to be manufactured at the end of the day. And that's the key takeaway here. You also have the ability to deposit on alternative materials, which is sort of a big area in printed electronics that we're going to be getting into. And then you can essentially reflow the components on the heated bed as well. This is just a quick project that was done by a student, an intern student actually, that came to work with us for a summer. He made an 8x8 LED cube. Also made some really cool flexible circuitry embedded in textile for high-tech fashion. So there you have it, a little bit of a preview of how it works and our office here in Canada as well. So what does this process allow you to do? Well, right now, the development process can look a little bit more like this, okay? So you go from having an idea, laying down your schematic, to prototyping with the actual machine. And like I mentioned, the key takeaway is that the machine will actually print something that is representative of something that is a final manufactured board, okay? So you don't end up in this strange kind of knowledge gap, essentially, where you're putting pins and wires together, but it's never gonna look representative of the final product that's going to be manufactured at that Chinese factory. And so, you know, the point of the V1 is not to replace mass manufacturing by any means. I mean, we'd never be looking to compete with China over here. The point is to get you to a product that looks like something that is final manufactured and get you there faster. And so throughout this process, the entire creative development cycle can look a little bit more like this. So you don't have a gap anymore. You go from having an idea to creating a design, to printing it and testing it. And then that loop just completes itself again and again. We do believe this now to be instrumental to the learning process. And you know, for all the students in the audience, I'm sure that you could experience being at school. And I know this was definitely my experience, being at school and being in some of the classrooms that were in a way fail-proof. It wasn't very difficult to go into those classes and to mess up a design, because everything was laid out for you kind of like Lego blocks, when in fact failure is instrumental to the learning process. It's very important to put something together and to see that it doesn't work and to wonder why it doesn't work, and to go ahead and rejig it and redesign it and try it again, and to fail again, and to again realize it doesn't work. And it's important for that cycle to repeat itself until you've gotten it right. And it's actually that process that is so instrumental to learning. And so that's why we're really kind of happy to be putting this tool on the desks of researchers and students alike, because they can actually see their design come to life, not work, and then that's okay. You can actually go ahead, you can start it all over again and find where the bug is until you've got it right, without, you know, having to ship designs off overseas, or without having to create something that at the end of the day just isn't going to be representative of the final product. All right, and so one of the best examples we have of implementing this technology on the desk of students is actually in Korea. We have managed to put a V1 on the desk of every student that is in a electrical engineering classroom. And it's been really, really cool to see what they've come up with it. Korea is for those of you that don't know, I spend quite a little bit of time there, and I'm blown away by what I learn there every time I go. But they invest very, very heavily in practical knowledge. And it's the chief of education actually in Korea that says practical learning is really the only kind of learning, when you can really get your hands on something and build something. And so it's been really neat every time I go there to see what the students create. This is just kind of a few things that I put together that were projects done by students. So this one over here on the right-hand side is a little robot that was created. Now, of course, the encasement, so his actual body was printed using a 3D printer. I believe it was an Ultimaker 3D printer. But the electronics that actually function him and make him move his little legs were actually printed using a Voltera V1 circuit board printer. And on top of that, you know, he was programmed to actually be to move on voice commands. So when the student speaks into the phone, he created this little app that makes him move his legs and makes him sit and makes him dance. And I mean, I just think it's adorable. And then over here to the left is just kind of a light box that was created using the Voltera V1, and then the box itself was, of course, 3D printed. But you can right away, right, start seeing the power of this technology parallel to 3D printing. It belongs right next to your 3D printer, so that you can now kind of, for the first time, not only create three-dimensional objects, you know, within the matter of an hour, but for the first time, you can create fully functional electronic products within a matter of an hour, which of course is very powerful, not only for learning, but for the industry as well, when they're kind of going through their R&D and developing new products. Kind of, you know, in addition to this, this additive manufacturing approach opens up a whole portal of electronic possibilities that we've seen in academia. So we've seen in the research lab that has kind of blown my mind, if I'm being completely honest. So conventionally, electronics are manufactured using a subtractive technique. So you'll start off with, you know, a board that's cladded with copper, and then that'll be dipped in a variety of different chemicals to remove away metal where you don't want it. Whereas, of course, we use the inverse approach to that. We start off with a bare board, and then we deposit material only where it's required. And what's really neat about kind of taking this additive manufacturing approach is that you're not limited to the conventional FR4 board, that green board that you'll find in all of your electronics. You can print electronics on a variety of functional materials, on flexible materials for kind of wearable technologies, on biocompatible materials for medical device applications, and a variety of different things. So we've kind of seen an explosion in this world that we call flexible hybrid electronics or printed electronics, where essentially it's estimated to be $30 billion by the end of 2020. And so we've been really kind of excited to see everything that's been going on in this industry, very popular in flexible displays as well. If you look at this technology right here, this is a really, really interesting device, medical device that was printed by one of the leading groups at Stanford University, Professor Bao's group. It's one of the leading research groups in wearable and medical technologies. And what you're seeing here, it's an electronic sensor that was printed on a type of biocompatible gel meant to be used for robotic skin applications. And so it's really neat what they do there. We know that, you know, if you could imagine a situation where you know, you've had a burn victim, for example, and they've required a skin graft. You know, it's a really big problem right now for them to be able to get a skin transplant. And so this group is doing a lot of work in creating a type of synthetic skin that can act like skin, that can feel like skin, that can have sensory input and output. And there's a lot of work going on in this area. However, this area requires the printing of electrically functional devices on biocompatible materials, not just conventional rigid FR4. Other really cool things that we've seen in this printed electronic space, I mean, this is kind of a fraction of some of the clients that we work with, but I've put it up here to try to kind of talk you through some of the other really cool stuff that we're seeing them do. For example, Nike, you know, we live in Canada, right? And I remember it was about a decade ago, Nike had sold us kind of this dream of heated jackets. And for anybody that might have been to Canada, you'll understand that it gets cold here. I mean, it gets really, really cold here. Unbearably cold, and you're kind of left putting on these big clunky jackets, you know, where you're kind of padded like the Michigan Man, and you're kind of just, it's not a very nice user experience. And so, about a decade ago, Nike was selling us this dream of heated clothing, where you'll able to be put on this kind of nice, functional, thin jacket, and it'll be self-heating. It'll come with a small battery pack, and it'll be self-heating. And I remember when that jacket came out, it was just, it was all these massive pockets were kind of integrated inside of it. And it had these big, control boards that were embedded in the sleeves and in the pockets. And it was basically like wearing cardboard. Not a very nice experience at all. But now, fast forward, one thing that Nike's doing with the product that's really neat is they're actually doing a lot more research in this area where you could actually print the flexible materials directly onto the fabric so that they can pull, they can stretch, they can flex, and they can heat up without having to actually print on rigid boards and then shove them into pockets. So really cool stuff there. We've got Tesla that's doing really cool things where they're printing on these flexible heated seats. If you think about a car, right, it's got a lot of curvature to it. It's got a lot of, three-dimensionality to it. And so they're printing these sort of flexible heated sensors that can be kind of laminated inside the curvature of the car. And a lot of really, really cool other things. Most recently, we've seen a lot of development actually happening towards COVID relief. So one of the issues that we've seen, especially over here when you kind of move towards the northern hemisphere, right, is a lack of components in ventilators. So, I mean, we know right now that there is a limitation to kind of ventilators, no matter where you are in the world. And one of the biggest problems is that ventilators are actually made with rare components that tend to come from Taiwan. And so everywhere, every institution that I could think of has kind of been working on their own developments where they're trying to design these ventilators that can be made from locally sourced components. So readily available components that could be found locally within their home country, not having to outsource them from abroad. And so this has been an enormous effort that's kind of been happening. And we see a lot of people that have been actually printing these ventilator boards in order to kind of accomplish what the prototype might look like. So really cool stuff that's happening there. And then, of course, just a few academic users. The only one that I want to point out here is Princeton University, who just 2 weeks ago right now launched the first ever printed circuit board into space that has been produced with additive manufacturing methods, aka our machine. And it was just launched into orbit in collaboration with NASA about 2 weeks ago on the Katherine Johnson spacecraft launch. So it was really cool. This was actually just a 17-year-old student that had been designing microsatellites. So there are these tiny little satellites that are meant to sort of download small amounts of data when in orbit. And so I actually want to introduce you guys to Shannon over here, because we went over and we did a little kind of case study on her. And so I want you to go ahead and meet her as well. Here we go.
Rather than seeing it as daunting, I see excited. What can be out there? I mean, there's so much that we don't know. Let's say like the laws of the laws of physics. What is life? I mean, it's life as we know it. That to me is what's most fascinating about it. My name is Shannon. I'm a freshman at Princeton. I'm planning to major in mechanical and aerospace engineering, and I'm from Virginia.
CubeSats were invented about 20 years ago by Cal State, San Luis Obispo, and Stanford. But they turned out to be pretty difficult projects, maybe more so than the original inventors expected. All of the challenges that you have with a large spacecraft are still there to some degree with a small spacecraft. So it's really one of the hardest projects that humans undertake is the design of an autonomous on-orbit spacecraft.
I actually found out about the project through an interest meeting for the Rocketry Club. you get to launch a satellite payload. It's going to be launched like during a resupply at the space station. I had done like a lot of camps where we designed like theoretical space missions before, and so the idea of being able to actually launch something that goes in space was really cool to me. And so I immediately was like, I really want to do this.
I'm setting up our small spacecraft design lab with a strong focus on enabling our students to make every piece of the spacecraft in-house here, to see something actually get built and get launched during their undergrad tenure. Before they graduate, they can see a small spacecraft through from conceptual design, through preliminary design review, through detailed design, integration, build, fabrication, all the way through spacecraft qualification tests, integration for launch, and then finally just orbital launch from the launch site.
I think it's pretty exciting because a lot of times if we didn't have something like the Voltera 3.1, if we didn't have the PCB mill, we would maybe get to design the circuit, but then we just send it off to a company. And I don't think I would have fully really understood what goes into a circuit, but now being able to actually see that like this is like this place where the electronics go, like using it actually helped me a lot to understand like what goes into a circuit and what components go where and all that stuff. So I think it's really beneficial to be able to see, will this stuff work in space? Because if it does, then that will be like a really great way for all these universities and even high schools that do make FinSat and CubeSat payloads to be able to use them. When I came in and was deciding between majors, working on this project really made me want to decide officially on doing aerospace.
All right. So we did that case study on Shannon and her laboratory at Princeton about 8 months ago now, and it was about 2 weeks ago that the microsatellites were officially launched into space, and they are currently orbiting Earth as we speak, downloading data. The first ever printed satellites ever to be launched into space. So this is pretty cool, because this was a 17-year-old student that is having a very, very large impact right now. And it's because, her and her lab, they had an idea that they were able to put into practice almost immediately after having that idea. So when you think of kind of the power of innovation, it's not to be slowed down. And that's why we've become obsessed with putting the proper tools into the hands of innovators, into the hands of students, brilliant minds, creative people, so that we can once and for all tear down the barriers of entry to hardware, to innovation, and really just put cool things into the world. So I invite you all to join the learning revolution. And yeah, I'm open to answering sort of any questions that anybody might have right now. Thank you very much.
Yeah, if anyone have any query, if you want to ask Katrina, you can put it in the chat. Yep. Thank you so much, Katrina. It's really inspiring, and I can see the machines spread across the globe, and the makers are really utilizing Voltera machine to build awesome circuits for multiple applications. So we look forward to multiple communities enabled with Voltera here in India. We started already introducing the machine to academia here, and we are getting good response. We have given a lot of demos to the faculty here. Most probably in a couple of months, we could see a Voltera machine utilized by the makers community across academia over here. Yeah, thank you so much for the inspiring session, and we love to have a couple of more sessions during our boot camp or an upcoming the Product Build-A-Thon event. Thank you so much.
Can't wait to see what you all build.
Yeah, thank you, Katrina. It was a wonderful session. We feel honored to have you here. So moving on next.
So we have a couple of questions. Yeah, Divya, go ahead, please.
Yeah. So we have Mr. G.S. Srikanth with us. So Mr. G.S. Srikanth is the founder and managing director of Allbit Technologies LLP. He have more than 15 plus years of experience in embedded systems, marketing and management administration. So he is much experienced in product development and
Your
developing the product.
voice is breaking.
Yeah, sorry, sir. So we feel honored to have you, sir. So Srikanth, sir, over to you.
Yeah. So let me just introduce Srikanth. Is a very motivated and inspired entrepreneur, and when I invited him for taking the session, he said like you want to take more sessions rather than I thought of giving a 1 hour kind of session to him as part of the bootcamp, but he loved to teach the students and share his 15 years of experience in electronic industry. And he runs a company called Albit Technologies in Bangalore. His specialty is into developing innovative product. He always takes up challenges thrown by the customers and starting from conceptualizing to the certification level. He provides services to the customers spread across the globe. And you ask any kind of component, Srikanth brings that component for you guys. And we are happy to have Srikanth sharing his experience in electronic product development to the students here. Thank you, Srikanth, for joining the session. Srikanth, over to you. Srikanth, we can't hear you. Srikanth, can you check your mic once? We can't hear you. Divya, can you hear me?
Yeah, sir. Just a second, sir. He has some problem. Just 1 minute.
Okay, please. So guys, people are asking about the program structure. Go through the link shared in the chat. The program structure is clearly mentioned. We'll have 3 days of boot camp.
Can you hear me?
Yes, we can.
Yeah,
yes, we
thank
can.
you. Thank you very much, Amar. So it's a pleasure to join with SmartBridge. So it's a very good platform for all beginners in electronics. They can learn more on and they can go in depth of electronics actually. So let me take my PPT session. Is that screen is available for everyone? Visible for everyone?
Yeah, sir, we can see.
Yeah, thank you. Thank you, Divya. So let us start from basic electronics because continuously I'm going to take from the component selection, basic electronics, how we are starting the design and how we are choosing the components, why we are into electronics and why we are choosing that technology especially. When we are moving into the next level, like tomorrow session and day after tomorrow session, like schematic development, design developments, and project creation. Then final thing is PCB and generating the Gerber, including the BOM. And final thing is the fabrication of the PCB and the component assembly. Before that, I want to go with some basic electronic, how electronics started, why we are into electronics, what is the relation between electronics and other technical subjects. Those things we will focus on this session actually. So let me introduce a quick introduction about me. So I have 15 years experience on embedded systems. So around 25 years experience of entire electronic industry. So initially the 10 years I have worked for a consumer and home appliances electronics as a service engineer. Then I moved into the embedded system designer. So I have started my own company, Albit Technologies LLP. So here we are going to do the new products like new design. It's a kind of research and development and design and development here. So there are plenty of things we are going to support to the customers, like the laboratory regulation approval, certification, and manufacturing supports. Some the general concepts what people brings to us, so we will bring it to reality in the electronic world. Let us start. How to enter electronics? This is absolutely, this session is for beginners. Let us start. How to enter into the electronics? What we need to focus when you are choosing the electronics in your college, when you are entering into the electronics in your colleges, so what they will ask normally. So they will always look into your mathematics and science percentage. Why they will, preferably why they will ask for mathematics and science? Because this electronics and electrical is purely based on your mathematics and science, because entire science, whatever we are doing, the mathematics and science is back to back, it's like a coin. So whenever you are depending on the science, you should be thorough with mathematics. So with the science and mathematics help, with the help of science and mathematics, we are going to move on to the electronics and electrical. So there is a, before starting to electronics, what we have technical subjects in our colleges. One is, as I told you, mathematics and science. So there is a one more subject is called mechanical. So after that mechanical, the electrical has introduced, then electronics came into the picture. This electronics is a combination of mathematics, science, and electrical and mechanical stuff actually. So before starting to electronics, we should know some basic electrical concepts, like how electrical started and what we are studying in electrical, what subjects we are studying in electrical. So I have made some basic few things how we can understand electrical. So there is a in
Srikanth,
that yeah.
Sorry to interrupt you. I don't know. There is a in your voice. Maybe it may be network issue or mic adjustment. Just please check once. Yeah.
So can you hear me now?
Yeah, I can. We can.
Is there any delay in the audible?
Yeah. Sometime we are getting the break in voice.
Yeah, just give me 1 minute.
Yeah.
Divya, can you hear me?
Yes, sir. We can hear you.
Hi, Amar, can you hear me now?
Yeah, sir, we can hear you.
Yeah.
Yes, we can. So that's clear.
Yeah, before starting electronics, we should know some basic electrical things actually. So one is insulator. Second one is conductor, then voltage, current, frequency, power, and energy. So why we need to focus on this actually, basic electrical. So insulator, what do you mean by insulator? Insulator is normally if you take a physics, so most of the times we know what is electrons, protons, neutrons, those things. So insulators, let me give you a quick explanation about this. So insulators, it does not allow electric charges pass through them. Okay, so this we want in future actually. So next one is the conductor. The conductor is a material which allows electric charges easily flows through them. Then voltage. So voltage is the amplitude level of your electrons. So how much it can amplitude, how much we need to amplitude the voltage. Then current, it's a strength of your electrons. Then frequency, how many times we can flow the amplification of voltage and current. Then power, how much power we can put it. Like it's a combination of voltage and current. It's like a Ohm's law. So if many of you know, energy is the per hour consumption, how much it is consuming and how much we are sourcing it. So it's a basic thing. Actually, many of you knows in the colleges and many of you studied about this, and it's just an introduction. So next thing is we want to know the measurement units for all these things. Insulator, yes, we are measuring in the ohms because it's in a high ohms like mega ohms or giga ohms. Next, the conductor will be in the milli ohms and it will be very low ohms actually. So voltage is we measure in volts, current is measuring in amps. The frequency is hertz and the power is watts and energy is watts hour. So the one per hour, how many watts we have consumed. Now, next thing is, because these are the basic things we need to understand. Next thing is some international system of unit, SI prefixes. This is very, very mandatory to understand before entering into electrical or electronics. There are so many symbols are there. In electronic technical terms, we are going to call it for 1000, what we are going to call, for minus 1000, what we are going to call, and for minus 1 lakh or plus 1 lakh, what we are going to call, or 10 lakhs, what we are going to call. So huge values, because these things we need to focus more on this, because most of the times we will use these words in our designs. Let us take an example. Kilo. Kilo means 10 to the power of 3. 1 into 1000. It's a 10 to the power of 3 is 1 into 1000 is a 1 kilo. So normally if I call it in ohms, 1000 ohms. So if for the short form, what we can use, we can call it as also 1 kilo ohm. For mega, 10 to the power of 6. 10 to the power of 6, if I, in spite of calling 1000 kilo ohms, I can directly call it as a mega ohms. So if suppose if I go for minus means if suppose if I want to make it 0.0001 ohm, so I can call it as a milli. It means the 10 to the power of minus 3 is milli. So please make a note of complete these things, because in future we are going to discuss with these particular prefixes units for the value of the components. Next, how to start electronics. So as you all aware about this, electronics is based on semiconductor and some basic electrical components. Beginners must know basic components and its properties. So what does this mean? So beginners, those who are entering to the electronics, or they are in first sem, second sem, or third sem, if those who don't know also they can learn, and those knows it's good actually. The thing is voltage, we want to know voltage, how many types of voltage we have, AC voltage and DC voltage. Current is same thing, AC current and DC current. Then the component wise, resistor, capacitor, inductor. So resistor, capacitor, inductor, this is actually from the electrical. So what do you mean by resistor and what do you mean by capacitor and what do you mean by inductor? So first we need to understand the properties of these components. What is resistor? Resistor is the material which is having the property of a resistance. So first we need to find out the definition for resistance. So if I tell, if I frankly telling about resistance, it's a general word. Resistance means we should avoid. That means we should force to stop something, and for limited energy. So better if it's which in electrical terms for resistor, which flows the opposition of electric charges. So up to certain limit. If I want to flow for 1 volt or 2 volt, so I can limit it. So if it is a direct shot, yeah, whatever we are getting the inputs as the same will be transferred to the output. If I want to put some barrier over there, so I need to use that particular property is called as a resistance. Then capacitor. Capacitor, which should have a capacitance, the material should have a capacitance property. So capacitance, how it will be built. So across the plates, there should be a storing of energy or some kind of transferring of energy. So with the, depends on the impedance of the material. So how we can give a definition for a capacitor? The capacitor is a component which allows AC, it can block DC. See, the beauty of the capacitor is AC it can allow, but when it is allowing the AC, definitely there is a reactance will be built. And for DC, it can block. That means if there is a polarity when you have in the source, it can block. So you should be very careful on these properties of these components, because once when you start the design, you will find out all these properties where we can apply and where we can use it. Then inductor. Inductor, definitely it works on AC, and it definitely it blocks in it works on AC, but it stops in DC actually. So it's nothing will work in DC. It's like a short. Next, the semiconductor component. Let us move on to semiconductor component. Semiconductor component means these are all purely basically electronics components like diode, transistor, and ICs. That diode is the first electronic component which is introduced. So before that, I want to tell you some of the things like what are the semiconductor? What do you mean by semiconductor properties? It's neither an conductor nor an insulator. What does this mean? So neither an conductor nor an insulator. It means when I apply some potential to the material, it should act as a conductor or it can act as an insulator. Insulator means it's an open link. So the first time the diode was introduced. So diode, which is having the PN junction. Most of you know that PN, what is the PN junction, or else you can go through the basic electronics theory. So with the diode, next it comes up with the transistor. Transistor becomes various integrated circuits. If you see the before silicon and germanium, there are the electronics was implemented on gases. Like many of you know about the vacuum tubes. So vacuum tubes technology is totally different. Now this is a silicon and germanium. Anyhow, germanium is almost, it is out of syllabus nowadays. The silicon is a major part which is nowadays coming up. All the components are coming up with the silicon technologies. Next, there is two more components are there. One is switches and terminals. These are all, it's a kind of electromechanical. So here the switch is comes with mechanical and as well as electrical and electronic. So switches are like electromechanical, and terminal, which is also a electromechanical component. So whatever the manual switches you will find, those will come, which will be called it as an electromechanical components. Let us next focus on some basic waveforms. Before entering into the electronics, let us focus on some basic waveforms. What are the types of waveforms we are using in our subject? So one is the major one is sine wave, square wave, triangle wave, and sawtooth wave. So most of the times we use sine wave in AC supplies and some kind of oscillations like in crystals and other things. The square wave, yes, nowadays it's very popular in digital electronics. The triangle wave and the sawtooth wave, normally we won't use it, especially on our regular platforms. But this sawtooth wave and this triangle waves will be used in some kind of RF filtering. So in the waveform, what we should focus, it's a like XY graph. So if you take a Y graph, it is nothing but an indicating the amplitude of the signal level or voltage level. The second thing is time with respect to time. So let us take an electronics definition after all these things. Electronics is a branch of science that deals with the study of flow and control of electronics or electricity or electric charges, and the study of their behavior and effect in vacuum tube vacuums. Actually, as I told you, the earlier version was vacuums and gases, and now the present one is semiconductors. And with the device using such electrons, like the electrons can pass from one end to another end, and which can be stopped. This control of electronics is accomplished by devices, electronic components. You can give a name called electronic component, like the SILI, which is the material, the components made with the semiconductors like silicon. So we can call it as an electronic components that resist and carry what that can do. Like basically what these components will do. Resists, it can resist, it can create the high resistance, low resistance, and carry the signals. It can carry from one end to another end, and you can select it, steer, and work like a switch, and we can store some data, and manipulate and exploit the electrons. So basically, this is a complete entire history of electronics from the basic scratch, what we have designed initial days, like some radios or calculators, from there to still today, whatever we have memory cards or whatever we have mobile phones, whatever we have laptops or computers, everything involved in this simple definition. So let us go for some basic things like DC current. What is DC current and alternating current, AC current? So what is frequency? So it's a simple definition. Direct current, it is stable, which is having only two polarity, plus and minus, like positive and negative. Next is a conventional kind of method. Then alternating current. Alternating current is which is having a 360-degree magnitude, which is having a peak to peak, like positive peak and negative peak, which start from zero and which touches the peak of positive and again come back to zero. Then again it is going back, going to 270-degree peak, and again it is coming back to zero. These things we need to focus more on: direct current, AC and DC voltages and currents. Then frequency. Frequency is also very, very important. The definition for frequency is number of cycles per second. Majorly, we are seeing this number of cycles per second in our AC voltage and AC current. So before starting to our electronic design or electronic things, we need to know the basic symbols, what it indicates, how if I take as engineering, how I can use the symbols and how I can create the symbol and what is the meaning of that particular symbols. So as I mentioned you, resistor. So some of the pictures I have put, like the resistor, how it looks, like some of the components, like it's a through hole component. There are for resistor, there is a color coding, and there are plenty of things are there. Some in SMD, we have some numbering system, how we can find out the resistor values. If for capacitor also same thing, the capacitor comes with their ratings. So all the components which comes with ratings and the values. Then diode, yes, diode also there is a picture actually, and there is a different diodes for different electrical specification and parameters. Then inductors. For transistors, these are the symbols, and MOSFET, some logic operational amplifiers or logic gates, we have different symbols. With that symbol, it is help us to build a schematic, and it's easy for us to understanding, and it's a standard, international standard symbols. There are many more symbols are there, like earth electric, then protective, signal ground. Then again cell, like batteries. So there is a lot of difference between a battery and a cell. Cell is a single unit, and battery is which is having multiple cell units. Like source, AC source, DC source. Then again resistor. Then again variable resistors. Then fixed resistors. Then capacitors, same thing, the capacitor and variable capacitors. Like this is the types of capacitors. Basically, most of the times in our college days, they will cover all these things. So just for remembering all the symbols and every electrical engineering symbols, we should focus on these symbols. When we are creating a schematic, that time we should use these symbols. It is easy for to understand for everyone. Then antenna, how exactly we are giving symbols for antenna. Then diode, again, then there is a loop antenna. So most of the times you might not seen that loop antennas. It was using in the old radios. And then coaxial cable. Many of you seen that coaxial cable with 50 ohms resistance. Then crystal, then fuse. All the symbols you should keep it in your memory. So before starting the schematic. There are loudspeakers. Then many more symbols are available in this. So you can download it from internet. So now electronics classified into two types. One is our analog electronics, like analog circuits you can call it as, and then is the second one is digital electronics or digital circuits. What is the difference between an analog electronics and digital electronics? So how we are dealing with this? To process analog signals, let us focus on next slides actually, how analog signals will be, how we are converting analog signals into digital signals and digital signals to analog signals. What are the analog signals? And all those things we can focus on next slides actually. Then before that, what is the circuit? So now we want to build a circuit. In electronics, whatever the platform we will see, everything is like a circuit. What do you mean by circuit? So let us take a definition for circuit. Circuit is a closed loop with respect to load. If you see an example, the battery and a resistance and a LED. So resistor and LED, which is in the closed loop to the battery. If I remove one link, it will be act as a components. It's not a circuit. So just you can see the components are placed, but the circuit is incomplete. Electronic circuit is a combination of series and parallel connection of an electronic component. What does that mean? See this, if you take a battery, the resistor and LED is a parallel to the battery. When you take a LED and resistance, it is a series to the battery. So sorry, so LED and resistor both are in series, but it is parallel to the battery. So like this combination we are going to use in the designs. Before making the circuit, we must know the series and parallel connection theory of each component. What does this mean? So we should study complete characteristics and the complete connection diagram and everything for the resistor, capacitance, and inductors. Because you know, many of you know that Ohm's law theory, how the resistors can be connected series and how the resistors can be connected parallel, and series and parallel combination, what will be the effect on that actually. So those things we need to focus more on the series and parallel connection theory. Next, what we do in electronics. So many of you have question, what we do in electronics, what are the topology we can use in electronics. Like the basic things are converters, like AC to DC and DC to AC we can do, voltage to frequency we can convert, voltage to current we can convert, current to voltage we can convert, the electrical signals into light energy, then light to electrical signals, then electrical signals to sound, sound to electrical signals. So the sound and light is a different source of energy for us. So from there, how we can convert it? If I take, for example, if I take electrical signals into light, so like just an example of LED. So we are giving the voltage and we are getting the light. From light to electrical signal. So light to electrical signal means So right now, everyone is aware about the solar. From the light, we are converting into electrical energy with the photo cells actually. Then electrical signals to sound. The best example for electrical signals to sound is your music system or speakers or some MP3 players or some laptop speakers or something like which is converting into sound or mic system, anything, public address system, all these belong into that actually. Sound to electrical system. This is for sound to electrical signals. It's the best example is your microphone. So when you are as a human, if I speak, then I will catch those audio signals and we can process into as a digital signal, and the another end we can again convert it into audio signal. Next process. What are the process we are seeing in the electronics like rectification, amplification, regulations, level conversion, and transformation. Let me explain you one more time. Rectification, amplification, regulation, and level conversion, transformation. So what is the meaning of rectification? So rectification means it's a rectifier, especially when I'm talking about the AC to DC. So you cannot directly use AC into electronics. So we need a rectification over there. So first we need to convert into DC voltage. AC to DC, how you will convert? That process is called a rectification, rectifier. So what are the type of rectifiers we are seeing? That's a half wave rectification, full wave rectification, and the center tap rectification. Why we use center tap rectification? All those things you can study in your courses, or you can join to SmartBridge for their regular courses. Then amplification. What we will do in amplification? Amplification is the process from the low signal to high signal. We can amplify the signal levels, like whatever it may be. If you take an example of a public address system, so human voice cannot go more than 10 meters or 20 meters. If you want to push your sound more than a kilometer or 500 meters, if you use an amplifier, like basically it is called an amplifier, which is an electronic device. The process is like from mic to speaker. In between that, there is a signal amplification. As I mentioned earlier, the voice will be converted into sound, will be converted into electrical energy, and it will amplify certain watts or certain gain, and it will be output is your speaker or my horn. Many of you know about horns. I think there is some kind of circle stuff with the some diaphragms. So basically, this amplification strength will be measured by decibels. If decibels is more, it's dangerous to human ear. So these things we should be very focused before doing any work. We should know the basic principles and basic process of the electronics. And there are some specification which involve to design your product. Next, regulations. What do you mean by regulation? Regulation is whatever the input, maybe it is a more than the threshold. Threshold, like if I give an example, there is a variation in your input supply. Input supply means if it is a input supply is some 7 volt to 12 volt or 7 to 20 volt. So that time you want to maintain a constant of 9 volts. So, or if it's a constant of 5 volts. So always regulator theory or regulation theory, what it will say, whatever you want the output. If I give an example of 5 volt, so you should choose 1.5 times more than the output voltage, your input requirement. Like for example, if it is a 5 volt, you should choose 7.5 volt to the maximum range, like 20 volt or 15 volt based on your requirement. So in between that, if it is linearly varying from 7.5 volt to 20 volt,
Sir, we can't hear you, sir.
Divya, can you hear me?
Yeah, sir, we can hear you now.
Okay. Then next level is level conversions. So what is the level conversions? Level conversions is like in electronics, if I say from step down to step up. So if suppose step down to step up means there are three topologies which is we are going to focus on. This is step up to step down to step up. So what is this? If suppose if your voltage is input voltage is 230, if you want to bring it down to 6 volts or 12 volts or 24 volts, this is called a level conversion. Maybe we are using transformer or regulators or rectifiers, everything we are using in that circuit. We will deal in depth once we start the particular session. So in this conversion, like from 232, if I bring it down to 6 volts, that is called step down converters. It's a level that 230 level 2, we are bringing down it to 12 volts. Then if I want to make it step up like if I want to use 12 volt source and I want to boost it up to 230 volt. So this is a different technology. So these are all called level conversion. The same thing we are using in for signals as well as amplification and as well as for voltage and current and frequency amplifications also. Then transformations. So what is the transformation? As I mentioned you earlier, from voltage to frequency, how we are converting, and from voltage to current, how we are converting, current to voltage, how we are converting. So like electrical signals to light source to electrical signals, those things we are calling it as a transformation. Now, how can I start electronic design? So we are into this session. So before starting the electronic design, we need to understand many more things in this. We should have a perfect vision what we want to develop. Basically, when you are developing something, you should know what you are going to do, what you are going to develop. If I give an example, you want to blink some LED with respect to time, like one LED is 5 minutes on and then another one should be off, then another one should be on for after 5 minutes and this one should be off. So those kind of requirements you should have a proper vision actually. So what I am going to do, see if I am designing for some multi-vibrator circuit or some amplifier circuit or some regulator circuit, so we should be very much stick on that particular subject. If I'm planning for an for a light circuit, and if I am focusing on the regulator circuit, then definitely there is a mismatch. Then finalize on the circuit requirement. So once your vision is clear, once your subject is clear, like if you want to build a regulator circuit, then you should have you should finalize on the requirement, like what I should regulate, what is the input voltage, and what the output voltage is expected from the source. Next, the prepare theory based on the requirements. What does this mean? The theory means what current I need, what voltage I require, and what I am getting from the input source. Okay. So one thing here I want to clear everyone, there is no source which can double your input power. Whatever we do the electronic design, definitely which is having the losses compared to input power. If, for example, if I give 80 watt input power, which is the combination of again voltage and current, the output will not be 80 watt. It will be maximum you can draw from that is, if it is keep it as a 70% or 80% efficiency, it will be like 70 or 60 watts. Those things we need to make a theory. What is the losses of the circuit and what is the internal consumption of the devices what you are using. Those things we should make a theory actually. Next, then make a block diagram before starting the design. So make a block diagram. What are all the things you should have in the design? Like the input source, whether it is a AC or DC. So make a note of that. Then if it is a AC, then what you need to do? You want to put it a rectifier circuit over there. Again, there is a level converter, like whether you are using the regulation basis, or if suppose you are using the AC from 230 to 12 volt, if you are converting some transformer with the help of the transformer, then again you are putting the rectifier. If you want to put a regulator, which is based on transistor, with the help of Zener diode, you can regulate and what is the output voltage. So it's just an example for the things. Next, the block diagram. Once if you finalize on the block diagram, then choose the proper technology suitable for the design. So proper technology means you know the input power and output power. You know the loss because of how you find out based on your theory. Definitely where there is a loss of energy, as well as there is a huge power dissipation over there. Power dissipation means there is a temperature rise in the circuit. So those things we should keep it in our mind. So proper technology, like if I want to take out the heat or noise from the design, what I should use? Like if you want to sustain for long term your devices, you need to add to protect heat, you need to add a heat sink over there. It's a aluminum solid block, so which can extend your component life actually. So basically these type of proper technology you should choose before starting the design. List out all your technical requirement and data. So the whatever initially I told you, that is a technical requirement. So before starting this design, you should focus on the maximum and minimum and nominal. The input supply, when you are applying it to the circuit, that time you should see the maximum level, how much it can go. Like if I give you an example of 12 volt, I want to give an input. So 12 volt can go 1.5 times. It's like a √2. So 1.5 times it can go high also, and it can come down also. Okay. So or else the minimum, if I keep a minimum voltage of 7 volt, as I mentioned you earlier, 7 volt, and the nominal is some 9 volt, the maximum is 12 volt. But the maximum means you should design it for 15 volt. There may be a spikes inside the input supply, or maybe some noise we can enter into the input supply, or because of some faulty component, you may receive more voltage. So better to have the maximum is different. So now in specification you will have a maximum, but when you are designing it, you should add up √2, 1.5 times you should add the limitation of your input voltage. Then output. So output requirement, like if you are drawing it 5 volt and 1 ampere current. So there also you should make a technical document, technical requirement. If it is exactly 5 volt, every time you cannot see. There is a drop and there is a positive and negative. Drops will be always there in the voltage, like that is called as a ripple. We can call it as a ripple. So maybe sometimes it can go 4.9 volt, or it may rise up to 5.1 volt. So those things you should focus on that. These technical requirement, you should make a document before starting the design. If the accuracy level or the error tolerance level is a little bit different, we should make that note also, and we should design the product, or we should design the circuit in such a level what they need exact output from the design. Next, choose the component based on the technical requirement. This is as it is, like as I mentioned you, the requirement specification and the maximum, minimum, and the tolerance of the output voltage. Those things, based on that we should choose the component. Like if I give you an example of resistor. Resistors are from 0.1% to there is a 20% tolerance. If you use 20% tolerance, what is going to happen? There is a variation is also, there is a lot of variation, 10 plus or minus 10 to 20%. So in that condition, we can use 1% resistor. So which can be reduced actually. Your tolerance will be reduced. But the difference is what? 20% and 1%. One is the major thing is cost, and the second thing is, yeah, some place we need this kind of percentage error resistors, like 1%, 5%, and 20%. Everywhere I cannot use 1%. Everywhere I cannot use 20%. So these things we should make a technical requirement document before starting the design. Next, what I need before starting the design. So some of the things we need to check, and we need to be sure that whether these are available with us or not, whether we can start it or not. So it's a kind of self-confidence, how I can build the design. So in that, when we are prepared the component material, component list, and technical specification, and your requirement is finalized, your technology is finalized, first we need to check it in the market, or the availability of component, whether whatever we have chosen, that components are available in the market or not. I mean to say that whether it is an absolute or it is an active state, or whether that particular semiconductor company is manufacturing that component, or whether they have stopped it. And okay, if it is available, and at how many days I can get it, whether it is an immediate or after 10 days or after 15 days. Those things we should be very careful before starting the design. Next, the component data sheet. This is a very, very important thing. When you are choosing the component, you should collect the data sheet from the manufacturer, component manufacturer. So why? Because we can get it all the technical details, like voltage and current and the temperature, then the characteristic of the component, everything will be mentioned even in your data sheet. So definitely, my suggestion is everyone should go with each component data sheet, and please read from first page to last page. Everything will be mentioned in the detail about the component in that particular data sheet. It is easy for you to understand how the component behaves. Okay, next the thing is designing tool. Designing tool, nowadays it's very familiar actually. So in olden days, the people used to draw the schematic, draw the symbol, everything using the paper and pencil and some geometrical units, and we are making the circuit design. Nowadays it's not like that. It's everything is computer based tools. We should know the tool which I can use it suitable for my design. So preferably everyone wants free tool with maximum benefits. Definitely we will provide you the very good tool for tomorrow session and day after tomorrow session, and it's absolutely free for everyone, and it's a best tool, and we will train you on that particular tool. Next, knowledge of the designing tools. So what does this mean as knowledge of the designing tool? Before using any tool, we should have a basic knowledge, and we should go through some tutorials or with the help of the tool, like it's a tool guidance you will get it actually. So from that, from scratch, how to start the project, how to create the project, how to save the files, what are the libraries are available in the tool, and how I can create my own library, and how I can connect the components internally. Those things we should know actually. So that is called knowledge of designing tool. So we should gain these things. Next, the fabrication process. What do you mean by fabrication process? After completion of design, like schematic, then library creation, and the net list, bill of material, all these things once if you are done, next you should move on to the PCB. So PCB is the core of the electronics. So where you can assemble your components, and you can evaluate whether what you have done is really that output you are getting it or not. So those things we should make a list. So to find out those things, this process is called a fabrication process. Especially this comes under fabrication, is the word comes for PCB development. So hard, whatever you're seeing the physically, those like as Voltera shown you, the tracks, the drillings, and the component pairs and all those things. This is called a fabrication process. The next one is assembling. Assembling is nothing but once your PCB is ready, whatever the components you have purchased from the market or from your vendors or from the online shopping or whatever it may be, that should be assembled on the PCB. How you are going to assemble? Via soldering. So using the soldering or some machinery tools, you can do the assembly. The final thing is you need to test it. So whether are you getting the expected result from the output? So whatever you are giving the input, whether you are getting the output, so that stage is like testing. And you can see the performance of the design, how exactly it is performing, and whether it is performing 100%, 90%, 95%, or 70%, or maybe it's not. If suppose it is not working, and if intermediately it is working, like sometimes it is working, sometimes it is not working. So those things, and you should fix it, and you should get a stable output from the device. This is called testing process, and as well as it is called as an evaluation process for your design. Next, let's see the step-by-step electronic design, how we are going to do this. Design requirement and document, which is already I have discussed you. Then component data sheet, which is already available. Next thing is we need to create the library for the components. How we can create the library for the components? One is for schematic. Normally we will call it as the library is called as a symbols. For PCB, we are going to call it as a footprint. So these are the two basic libraries for schematic and the PCB. Okay, so the symbol, yes, definitely we should create, as I shown you earlier my slide, like basic symbols, international standard symbols, what we are using for resistor, capacitor, transistor, ICs and gates. All those symbols you should create it and keep it ready and store it in the one location. The footprints means physically when you are seeing the capacitor, IC or transistor. So based on, there is a mechanical dimension for that actually. If you take a transistor is having the 3 leads. In that 3 leads, each lead is having a dimension. Like if it's a 0.5 mm thickness of the lead, how much we should create the pad, and how I can solder just, the transistor on the PCB. Those things we need to create it, and we are going to learn it in the creation of footprint and symbols in the next session actually. Next is schematic design. So once these libraries and everything is ready, so we should start with the schematic design. Then after the schematic design, we should make a bill of material. What do you mean by bill of material? Bill of material means whatever the components we have used and those component values and the footprint. There is a package for each component. Like for example, for through-hole components, we will call it as a deep through-hole component, some TO93 package, some 220 packages. There is a lot of packages discussion will come actually. So for SMD, so surface mount devices, yes, for that also we have different. The surface mount device means it's a completely on your surface, means the PCB. On the top of the PCB, you will place this without any holes. So through hole indicates that, yeah, you are passing the leads from top to bottom. Okay, so for surface mount, yes, you are directly placing on the top actually. Okay, so then next, netlist creation. What is the meaning of netlist creation? When you are connecting one component pin to another component, there should be a net. Net means the connection is called as a net. So that net should be created before starting the PCB, because the PCB tool cannot understand without saying your nets. That we will focus it on the when we are starting the schematic and the PCB design. Next, finally, is PCB design. How to import all your concerned symbol and footprint into the PCB design. How we can create the board dimensions, and what are the mechanical things we can fix there, like holes and mechanical fixture, how we can fix it on the PCB, and what is the dimension you are going to look for the PCB. Like the PCB should have a dimension, like length and breadth or some kind of circle, anything you can make. For that, in detail discussion or in detail class, I can show you the PCB design, how we should start. Like what are it called actually. So when you are giving the board cutout for a circle or square rectangle, so what is that particular content is called. Then what are the things when you are seeing some PCB, there are some component reference values will be available on the PCB. How we can create it, what is that layer called. Then the soldering pads we will see. That soldering pads, what we are going to call for that soldering pad layer. So those things we are discussing in the PCB design tool. After once your component placement, routing is completed, your entire PCB design is completed, we need to generate a Gerber. What is the Gerber? Gerber is something, it's a design tool is different format. The Gerber tool is different format. Like it's an some other format, extended format for the machines. So in that we have standard Gerber formats. Those in that format we should convert it and give it to the fabricator. Like Voltera has shown the proto PCB fabrication machine. With that, what we can do, they have some their machine is having some format which will be easily accept. So that format we should convert it and give it to them, and it can be converted to your PDF format, or it can be converted to any other format, but it should be supported to your, especially on your fabrication machine. Then final thing is the PCB fabrication will be done by the PCB fabricator, like Voltera machine or some other X vendors from the outside. Next, component assembly. Once if you receive the PCB, as I mentioned you, the component assembly, and finally testing and validation of the design. Okay, thank you, and hope tomorrow session we will start schematic and these things on online session. So everyone will have a chance to learn that. Initially, I will tell you how to start the project and how to import the libraries, and some of the libraries which is provided by the vendor, how I can import it into the my tool design, and how to install the tool, and what are the design rules, and how better I can make the schematic which is understandable by everyone, and if it is understandable by myself. So those things we can focus on tomorrow's session. Thank you all.
Thank you, sir. Thank you for your wonderful session. So, guys, tomorrow we'll be doing hands-on practicals with KiCad software. So you guys need to install the KiCad software. Okay. So if you have any doubts in installing it, I'll tell you in few minutes. So in the meanwhile, I'll just show you feedback.
Divya, 1 minute. So yeah, before starting tomorrow's session, you can install KiCad software for hardware design. I think Divya can share you the link actually. So it's a free software. Don't worry. You can develop schematic and PCB, whatever you want. And it's a very beautiful software. You can see your PCB, exact PCB 3D view in that particular software.
Yeah, sir. So guys, I am pasting, so we have pasted a feedback link. You guys can give your feedback there. And yeah, I'll show you. Just wait for 2 minutes. So I have posted you one, so I'm posting one link. So you can go to this link. So I'll share my screen and I'll show you. Just a second. Yeah. So see guys, if you open the link which I have posted in the chat box, even we have mailed you that link also. Okay. So this is the KiCad.org. This is the official website of KiCad. So you can go there, and here you can see in this download option, we have many options. Okay. So if you are using Ubuntu, you can select this option, and if you are using Windows, you can click on Windows. So now when you click on Windows, it will be redirected to other page. So here you have 3 different options. So you need to choose the third one. So whenever you choose the third option, like whenever you click on it, an exe file will be downloaded. So whenever you download this file, just double click on it, then the software will start installing. Clear, guys? So even I'll post this link and everything in the Telegram group also. Yeah. So we have pasted the feedback link in the chat box, guys. Now can you hear me now?
So there is Divya, can you hear me?
Yeah, sir.
Yeah, there is a one more information. There are plenty of fundamental things which we are missed in this session because of the short of time. In 1 hour, I can give you the shortest and quickest introduction about electronics and the component level. So those who are interested, they can join with the internship course or some kind of course with the SmartBridge, and they can learn fully, because for complete fundamental electronics and technologies and topologies, if I want to explain it, at least it will take minimum 6 to 9 months, because you should understand, once if you know the fundamental of the subject, you can build anything over that actually. So this is my request, or you can go through some technical theory subjects or some design examples. So with that, with the help of that, you can achieve anything in your life, like whatever the complexity IoT products, or it may be, if someone feels like it's highly impossible for us to do this, and only the brilliance can do this. So don't keep those kind of things in your mind. And once if you are fundamentally strong, you will be also in that position. This is what I am going to tell you, all the attenders.
Yeah.
The second thing is for KiCad, there is a 32-bit version and 64-bit version available. Please check your OS whether it is a 32-bit or 64-bit. So based on that, you please download the exe file and install that. Yeah, thank you all. Let us meet on tomorrow's session.
Yeah, sir. So guys, regarding internship, we'll let you know. Okay. So I hope you guys have the feedback link and also the download link of the KiCad. So for tomorrow's and day after tomorrow session, you need to have laptop, guys. You can't join in your mobile phones because it is entirely a hands-on practical session. Okay. So if you guys have given your feedback, you can leave the session. So don't miss tomorrow's session, guys. So it will be like we'll be creating a schematic for a small circuit, and also like you'll be dealing with some basic concepts of schematic diagrams and all, and even you'll be creating a PCB. Yeah, you can even use your PC, guys. Yeah, guys, we are pasting the feedback link once again, and also we'll post that in the Telegram group also. You can give your feedback there. Yeah, guys, any one who is interested can do the internship. Okay. So even if you are in your first year, no matter, you can do your internship. We'll tell you more details about the internship and its cost and everything. Like either it is free or cost. We'll tell you on the third day. Okay, at the end of this build-a-thon.